In the previous video, we learned about field-oriented control, also called vector control, where the drive uses an encoder to keep track of where the rotor is so it can optimize the orthogonal current components to get superior speed and torque control of the motor all the way down to 0 RPM. Now it turns out, as long as there's enough of a magnetic field in the motor's rotor for the drive to track it, the drive can do a really good job of controlling the motor without using a sensor, which is why we call it sensorless vector control. Of course, for the rotor to have enough of a magnetic field for the drive to work with, it has to be rotating faster than some minimum speed. Let's show that graphically. Above some minimum speed or frequency, the drive can use sensorless vector to dynamically control the current to optimize the speed and torque of the motor. Parameter 182 contains that cutoff frequency, and it defaults to 30 RPM, which for our 60 Hz setup would be 1 Hz. The programming manual for the CFW500 drive recommends staying above 18 RPM, which for our 60 Hz motor would be around 0.6 Hz. That's pretty good, especially when you compare it to volts Hertz, which struggles below a few Hertz. What happens if you try to run the drive below that cutoff speed? Well, the drive automatically drops out of sensorless vector and goes into something called IF mode. That is, it simply pumps a fixed amount of current into the motor. It's kind of like volts Hertz, except it controls the current instead of the voltage. The scalar current value sent is in parameter 183. Now this is the percentage of the motor's magnetization current in parameter 410, which is determined during tuning. It's not a percentage of the rated current. By the way, if parameter 182 is less than 3 RPM, the sensorless vector will always be on. It won't transition to the IF mode. Other than that low frequency stuff, this is identical to the vector control with the encoder we did in the previous video, except there was no cutoff. Full vector with the encoder could control the motor all the way down to 0 Hz. Let's do an example. I'm using the exact same setup as the previous video, except I removed the encoder wires, just to be sure we're really using sensorless vector mode. Since the hardware is identical, the only difference between the two is the mode we're operating in, so we can do a true apples-to-apples comparison. And once again, I need to stress that all inverter duty or inverter rated motors are not created equal. It's critical that you choose the right motor for your VFD application, and in particular, choose the right motor for the mode the drive is using. To get the most out of these vector control modes, you need to have a motor that's optimized for vector control. This is what we need to do. It looks a lot like the list we had in the previous video, doesn't it? The only difference is we don't have an encoder module to install, we need to tell the drive we want to use sensorless vector control, and we'll be using a different tuning method. I've also added the sensorless vector low frequency cutoff parameters for reference. And there's one additional parameter we're going to need in just a minute. I'll gray out all of our reference and read-only and default parameters so you can see we really don't have much to do in this block of tuning steps. Okay, let's power up the drive. Uh-oh, we have a fault. What's going on? Well, fault 79 tells us the encoder isn't wired correctly. Remember, I have the encoder module installed, but I removed the wires to be sure we weren't using the encoder in this demo. So yeah, the encoder isn't wired correctly. Now we could remove the encoder module, but we might be using some of its IOs or have plans to upgrade to an encoder in the future. We could ignore the fault, but that's annoying. Instead, look at this. Parameter 343 is a mask where we can turn off things we don't need. In particular, setting parameter 343 to an 87 hex turns off the encoder module fault. Hit this to clear the fault, and yep, it's gone. Perfect. Now don't forget to turn that back on when you decide to add the encoder back in. I reset this drive to factory default before I started the video. If we did it again right now, well, we would have to go disable that encoder fault bit in parameter 343 again, so let's not spend time on that. The drive defaults to volts Hertz mode, so if I hit run, it spins up to its default 3 Hz min frequency. Now this is important. Verify that the motor is spinning in the same direction as this arrow on the display. If not, remove power from the drive, swap any 2 motor leads, and try again. The motor should now be spinning in the correct direction. Ours looks good, so I'll hit stop. Drop into the parameter groups and scroll down to the startup group that walks us through configuring the drive just like we did in the previous video. That brings up parameter 317, where we tell the drive we want to configure it for one of the vector or field-oriented modes by setting it to a 1. That sends us to parameter 202. We set that to a 3 to tell the drive we want to use sensorless vector mode. This is the line voltage we expect, the service factor is fine, and the default rated voltage is fine. The motor's nameplate says it's rated for 3 amps, so I'll enter that here. 60 Hz is what we're using, and the motor's faceplate says it's rated for 1725 RPM, so I'll enter that here. This is the motor we're using, and we're not using an encoder, so we don't care about this guy. I'm a little surprised this sensorless vector mode would even ask for that. The motor is self-ventilated, and we're done. Go to parameter 408. We want to use mode 2, which is the best tuning we can do without a sensor. Now this mode expects there to be no load on the shaft. Since this pulley really isn't much of a load, I'm going to leave it on to make it easier for you to see when the shaft is turning. Bring up a stopwatch and fast forward the video. When tuning's done, the drive restarts. That took around 3 minutes. Not bad at all. I'll hit run, and the drive spins the motor up to its default min frequency of 3 Hz. Let's go to parameter 133 and change the min frequency to 0 Hz so we can mess around with the lower speeds. Now remember, sensorless vector can't go all the way down to 0 RPM, and we use the default cutoff of 30 RPM, which for our 60 Hz motor is 1 Hz. That means at 1 Hz, the drive should switch over to the IF mode where it just injects a fixed current. So watch the current bar as I scroll down to the 1 Hz cutoff for sensorless vector control. It's running at about 3 bars, or 30 to 40% of rated current. If we go below that 1 Hz cutoff, yep, the current jumped to 5 bars, and it stays there. Why? Well, because we told it to turn off sensorless vector below 1 Hz and switch to the IF mode. In that mode, the drive is supposed to inject 120% of the motor's magnetization current. That's in parameter 410, which we see as 1.7 amps. 120% of that is 2 amps. If we go to parameter 3, which shows us the current being output, yep, the drive is forcing exactly 2 amps into the motor. Exactly what we expect. Let's go back up to 2 Hz where we know the drive is using sensorless vector control. And just like with the full vector control using the encoder, if we watch the current on the bar graph and I grab the pulley, we see the drive try to do everything it can to get the pulley moving again at the RPM we requested. Volts Hertz won't react like that. So it looks like sensorless vector is doing its thing. Cool. And if we stop the motor, we see it won't free spin, and the drive is still sending current out. Again, just like in full vector control, the motor's magnetization current defaults to always on when in any vector mode, even when the motor stopped. If you don't want to burn that energy while the motor stopped, you can tell it not to inject current while the motor stopped by going to parameter 181 and setting it to a 1. Now we see the current output is 0, and the motor's rotor is free to spin. That ought to be enough to get you started, but there are a number of things you need to be aware of if you want to take full advantage of the vector control modes, like how to choose the right inverter duty motor for your application. All motors are not created equal. Why the motor full load amperage has to be above some minimum. Should you tune with the motor warm or cold, and why? How to minimize power consumption when in vector control mode. How to deal with overloads. How vector control affects braking, and any other loose ends I think of. Join us in part 3 where we'll show you how to get the most out of using the vector control modes. Meanwhile, click here to learn more about the WEG CFW500 drive. Click here to learn about Automation Direct's free award-winning support team options, and click here to subscribe to our YouTube channel so you'll be notified when we publish new videos.